Hi, I'm Dr. Incognito. In this video, we're going to discuss the different types of discontinuities. So first, let's recall the definition of continuous. So to say that f of x, the function, is continuous at x equals a, that means that the limit as x approaches a of f of x is equal to f of a. The limit is equal to the function value. So it might look like this. If this is the point a comma f of a, then the limit as x approaches a of f of x is going to be f of a. You can, for a continuous curve, you can draw the curve through the point a comma f of a without lifting your pen from the board. So we want to look at what happens when a function is not continuous. So the limit as x approaches a of f of x, for whatever reason, is not equal to f of a. If that happens, then we have a discontinuity. We have a discontinuity at x equals a. And there are a few different reasons that this could happen. Why might it be true that the limit does not equal the function value? It might be the case that the limit as x approaches a simply does not exist. If the limit does not exist, then it can't possibly equal the function value. Another possibility is that maybe the function value does not exist, so f of a is undefined. So in other words, a is not in the domain of the function. So maybe a is not in the domain of the function, so f of a would be undefined. If f of a is undefined, then the limit will not equal the function value. Another possibility is that the limit exists and that f of a is defined, but they just simply don't equal to each other. But they simply are not equal to each other. That can happen as well. So let's look at some of the possibilities. There are three main types of discontinuities. They are called a jump discontinuity, a removable discontinuity, and an infinite discontinuity. So first, let's look at the jump discontinuity. In a jump discontinuity, we have a situation like this. Let's say this is x is equal to 2, and here's our curve, and that's a height of 1. And then our curve picks up on the other side over here. So this curve is y equals f of x. The function consists of these two separate pieces. We have a jump here when x is equal to 2. This is a jump discontinuity. And what's happening here is that the limit as x approaches a does not exist. You see, in this situation of a jump discontinuity, the left side limit as x approaches 2 in this case, the left side limit exists, it's 1, and the right side limit exists, it's equal to 3. So the left and right side limits both exist, but they're different values. And so the two-sided limit does not exist because the one-sided limits have different values. Notice again here the detail that in the definition of continuity at x equals a, the limit that we're investigating is a two-sided limit. So if the one-sided limits disagree, as in the case of a jump here, if the one-sided limits disagree, then the two-sided limit does not exist, and hence the function could not be continuous at x equals, in this case, 2. So in this situation, we say that the function f of x has a jump discontinuity at x equals 2. And the size of the jump is the difference between these two one-sided limits. The bigger one minus the smaller one is the size of the jump. It's a jump of 2 units. One other remark about this. In this particular picture, I put a closed dot right there, so that means that in that situation, f of 2 was equal to 1. But that never came into play. Since the limit here did not exist, we didn't even have to worry about what the function value was, or even if there was one. So if this were an open circle, we would still have the same conclusion that we have a jump discontinuity at x equals 2. Or if this, or if there were a dot, say there, so that if f of 2 were equal to 2, then we would still have a jump discontinuity. So the jump discontinuity comes from this limit not existing because the left and right limits are different numbers. So now we'll look at the removable discontinuity. Removable. So that situation looks like this. So suppose this is y equals f of x. Let's suppose that's 2 and that's 3. So here we have the limit as x approaches 2 of f of x is equal to 3. As x gets closer and closer to 2, on either side, then f of x is going to get closer and closer, the height is going to get closer and closer to 3. As x approaches 2 from either side, the corresponding points on the curve are getting closer and closer to that open circle, which is at a height of 3. So we can conclude that the limit as x approaches 2 of f of x is equal to 3. However, f of 2, the input here is 2, f of 2 is undefined. So in other words, 2, there's an open circle there, and there is no point on the curve corresponding to x equals 2. If you were to draw the vertical line x equals 2, it does not intersect the curve anywhere. So f of 2 is undefined. 2 is not in the domain of the function, and so therefore the function is not continuous at x equals 2. There is a discontinuity, and this type of discontinuity is called removable. The key feature for a removable discontinuity is that the limit exists. The limit does exist. In the jump discontinuity, the limit did not exist. In the removable discontinuity, the limit exists, but for whatever reason, there's not a dot where we want there to be a dot. Another possibility similar to that is you draw basically the same picture. Let me put the dot down here. So this is 2 again, this is 3, and let's say this is, let me make the dot lower and make it 1. So in this case, the limit as x approaches 2 of f of x, this is y equals f of x again, this limit is 3, and f of 2 is equal to, now a vertical line does intersect the graph because this dot is on the graph. So f of 2 is defined. This is the point 2 comma 1. F of 2 is equal to 1. So here the limit exists and the function value exists, but they're just different. Clearly the limit as x approaches 2 does not equal the function value. And so again, we have a discontinuity, and it's of the removable type. The key feature in the removable type is that the limit exists. So in this case, the limit exists. The function value also exists, but they're different. And in this case, the limit exists, but the function value is undefined. So that's a removable discontinuity. The limit exists. The reason it's called removable is because if you wanted to make a continuous function, all you would have to do is define f of 2 to equal 3. So instead of putting this dot here, if you just put it right there, then you would have a nice continuous function. This jump discontinuity situation, you can't fix by just putting a dot somewhere on the graph. So you can't remove this discontinuity, but this discontinuity could be removed. If you want to remove the discontinuity in this graph, you can do so by adding a single point. And lastly, we have the infinite discontinuity, which indicates the presence of a vertical asymptote. So the infinite discontinuity quite simply, there's an infinite discontinuity at x equals a if the limit as x approaches a from either the left or the right is equal to either plus or minus infinity. So if either of these occurs, then you'll have an infinite discontinuity. You will have in the graph a vertical asymptote. So let's say this is 2 again. Let's draw the vertical asymptote. And let's just say that the curve actually, for whatever reason, is nice on the other side of the asymptote, and even at the asymptote has a value there, 3. So here we see that f of 2 is equal to 3, so the function is defined at 2. However, the limit as x approaches 2 from the left of f of x is equal to plus infinity. The left side limit is plus infinity. The right side limit is 3. The right side limit is the height 3. So the left side limit and the right side limit disagree in the same as the jump discontinuity. The left and right side limits disagree, and that means that the two-sided limit does not exist. But rather than saying that we have a jump discontinuity here, since one of the one-sided limits was infinite, we call this an infinite discontinuity. It's kind of like an infinite jump. And it indicates the presence of a vertical asymptote. So that's an infinite discontinuity. One other example of an infinite discontinuity. That's 2 again. Let's say we have this situation. We could let f of 2 be 3 again if we like. Let's put this dot on the curve so that f of 2 is equal to 3. Now the left side limit and the right side limit are equal. The limit as x goes to 2 from either side, maybe equal is not the right word, they're the same, they're plus infinity. So we don't really have a jump per se in this situation because the left side limit and the right side limit are the same, but they are infinite, and so we have an infinite discontinuity at x equals 2. So an infinite discontinuity indicates the presence of a vertical asymptote in the graph. Okay, so those are the 3 types of discontinuities. There's the jump discontinuity where the one-sided limits exist, but they're different. There's the removable discontinuity where the one-sided limits agree, but and they're also a number. So the one-sided limits agree, but they're not a number. So for the removable discontinuity, the one-sided limits agree and they are a number, but for whatever reason, the dot on the graph is not where you would want it to be. And then you have the infinite discontinuity where the graph has a vertical asymptote. Okay, thank you for watching.